All right, so assignment 3-2, let's do the assignment together. So in question number 1, you're given an equation and you're asked to do some calculus with it, as well as understanding the end behavior would be helpful. So I'm going to take the derivative here. This is 3x squared minus 6x. I'm going to make it equal to 0. I want to know where it's increasing and decreasing, where the points, where the turning points are. I'm going to factor out to 3x, and then I'm going to solve it. So this gives me the answer 0 and positive 2, and then those are called critical numbers. Then I'm going to draw a number line, and on that number line we'll have 0 and 2. If I plug in a negative number, it's a negative times a negative, which is positive. All the exponents are odd, so the sign changes as you go across. So every time there's a critical number, the sign changes. We have a maximum and we have a minimum. So we're going to write down that our maximum, our local maximum, is at 0. If I plug 0 in here, I get the answer 5. We also have a minimum, a local minimum, at 2. If I plug 2 in here, I get 8, take away 12, negative 4 plus 5. I think it's 1. Double check. Next, I'm going to do the second derivative. So these are points on my graph, and then increasing, decreasing, increasing. The second derivative is 6x minus 6. If I solve that, x is equal to positive 1. Draw a number line. If I plug in 0, the answer is negative. If I plug in 2, the answer is positive. So there's a point of inflection at 1. And if I plug 1 in, I get 1 take away 3, negative 2 plus 5. So at 1, 3, there's a point of inflection. And now I'm going to sketch this right here underneath. So 0, 5, 1, 2, 3, 4, 5, 2, 1, and 1, 3. All right. So 0, 5, 1, 3, and 2, 1. So those are the points I know. Understanding concavity and end behavior. So x cubed is the power term. So the right end goes up and the left end goes down. And now we just do concavity. So it increases and it starts concave down. So it increases, it turns, and then it stops. So this is concave down all the way to 1. It increases to 0, and then it starts to fall after 0. So that's that match. The left end goes down and the right end goes up. Now it's concave up, turn, and you sketch the graph. Number 2. We're going to do the same steps here. So I'm going to take the derivative. I'm going to make it equal to 0 and solve it. When I try to solve this, I get x squared equaling negative a third. So there are no critical numbers. That means it's monotonic, so it's only increasing or only decreasing. So no, whatever number I put in for x, the answer will always be negative. So this function is only decreasing. When I take the second derivative, so there's no turning points. It's negative 6x, make it equal to 0, and x equals 0. So the concavity has one point of inflection. If I put in a negative number, it's positive and then negative. So it's concave up and then concave down. Again, the power term is negative x cubed. So the right end goes down and the left end goes up. And now we're going to sketch that. So the only point that I'm going to put down here is at 0. And if I plug in 0, I get the answer 1, so I should write that down. So the point of inflection is at 0, 1. And then concavity. So it's concave down and then concave up. Oh man, what did I do wrong? Don't do that. End behavior. Let's try it again. And let's do it right. Silly me. So if I'm going to sketch this, what did I do wrong? So it's concave up and then concave down. Let's do it right, right? That's the right one right there. Ignore this. Pretend I didn't do this. Number 3. In number 3, we're going to go through the same steps. Take the derivative. After you take the derivative, make it equal to 0. Factor this. So that's 4x squared. That's x minus 3. So the two answers are 0 and 3. So when I draw a number line for the first derivative, 0 and 3, be careful of the even exponent. So when I plug in a negative number, it's a positive times a negative. And then that sign is going to stay the same because of the even exponent, and then it will change at 3. So we have one turning point, and that's at 3, and it's a minimum. So we have a relative minimum at 3, and then you would plug 3 into the actual equation to find the y-coordinate. And if you plug 3 in, you get the answer negative 11. Next, we're going to do the second derivative. That's 12x squared minus 24x. Make it equal to 0. Factor out a 12x. The two answers here are 0 and 2 for our number line. Those are the critical numbers of the second derivative. Again, these have odd exponents, so it's just going to change. So it's a negative times a negative, so which is a positive, and then the signs change as they go across. So we have points of inflection at 0 and 2. So 0 gives me the answer 16. And 2, if I plug it in, gives me the answer 0. There you go. All right, so let's do it. So now we're going to take this information here and we're going to graph it. Oh, I dropped my pen. All right, 3 and what? Negative 11. Let's pretend it's here. And then 0 and 16, which is a little bit higher. Pretend it's there. And then what's the concavity? And so it decreases all the way to 3. But the concavity. So first, it's concave up. And then it's concave down. And then again it's concave up, and then this is a minimum. In the end behavior, both ends go up. So there's the graph. So the power term is x to the 4th, so both ends go up. So understanding end behavior, turning points, points of inflection, concavity, increasing, decreasing, putting it all together. Number 4. For number 4, we're graphing again. So this is a parabola, and so you've graphed a parabola before, but with calculus tools, what would it look like? So if I want to find the intercepts, those are pre-calculus tools. I'm going to factor and then solve it. So we have intercepts at 4 and negative 2. When I take the derivative and make it equal to 0, when I solve it, I see that at 1, if I do a number line, if I plug in 0, it goes negative to positive. So 1 is a minimum, which is our vertex. And if I plug 1 in here, I get negative 9. And then you'd graph it. Oh, if I did the concavity, does he even talk about concavity? No, not for 4 and 5. But if I did do the concavity, it's concave up. It would just be positive 2, and it stays concave up. So 1, negative 9, and then was it negative 2 and 4? And then draw your parabola. So it's concave up. It has these intercepts. Oh, I said find the y-intercept. So if I plugged in 0 here, the y-intercept would be at negative 8. So this right here is negative 8. And you did it. Number 5 is really similar. And number 5 says, what happens if you put absolute value bars? How would that change the graph? And then find all the other information by it. And so the absolute value bars, what it does is take the graph that's below and reflects it up. So we're going to take the vertex and reflect it up. So it's at positive 1 and 9. And then our intercepts would stay the same. And so this is what the graph would look like. And so it comes down, so this part that was underneath got reflected up. And so it kind of looks like a W now. So if I asked for the intercepts, they stayed the same. The y-intercept changed. It's now positive 8. And the minimum has now become a relative maximum. So it's not even an absolute now because of the reflection. So there's a relative maximum at 1, 9 in terms of a point. All right, number 6. Find the relative extrema points of inflection, end behavior, and graph without a calculator. So I'm going to find the derivative by doing the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. I'm going to simplify this. If I go x squared times 4x, that's 4x cubed. If I go 2x squared times 2x, that's 4x cubed. Let me show it to you. So this is 4x cubed plus 12x minus 4x cubed. So I just want you to show you that it does simplify, that this crosses out, and that really the derivative is just 12x over x squared plus 3 squared. All right, so what do we get from the derivative? The critical number, look at the numerator equal to 0. So the critical number is 0. That's it. And it goes negative, positive, so that at 0 is a minimum. To find the y value, you come back here, plug in 0, and the answer is 0. So at 0, 0 is a minimum. The second derivative is given, so I'm just going to write it down. That's a weird y. So that's negative 36 Now, x squared take away 1, I'm just going to do a difference of squares right away because it'll be helpful to me. So if I solve it, the two answers, if I take the numerator equal to 0, would be -1 and +1. These have odd exponents everywhere, so the signs are going to change as soon as I find the first one. So a negative times a negative times a negative. It's a negative over, now if I put a -2, it'll be positive. So a negative over a positive. So it's going to go negative, positive, negative. Concave down, concave up, concave down. So we have point of inflections at -1 and +1. So to find the y-coordinates again, -1 and +1 give you the same answer. This is an even function. It gives you 2 over 4. That's a half. Both -1 and +1 get you a half. And now put all that information together on a graph. Oh, and the end behavior. To find the end behavior, power term over power term. Notice if I look at the power terms, divide them, and you get the answer 2. So the end behavior is y equals 2. What else do I know in my graph? 0, 0 is a minimum. And then we have 1 and a half and -1 and a half. And now the concavity. So this is concave down and decreasing. So we're following, it's decreasing concave down at -1. It changes to concave up and still decreases, and there's a minimum. So just as you draw it, it decreases to 0 and then it increases. It's concave down, then concave up, and then concave down, and the end behavior goes to 2. And you did it. Number 7. Find the domain, extrema, asymptotes, end behavior, and graph it. There are no points of inflection. So I'm going to take the derivative right away. I think it's helpful to write this as x squared over 2x and 1 over 2x for the next derivative. Oops, that one ran out. So this is the x and the x squared cross out. So this is really 1/2 x, and this is 1/2 x to the -1. So the derivative of this is 1/2 minus 1/2 x to the -2. I don't know if that was more helpful or not. If I did it the other way, it would be the bottom times the derivative of the top minus the top times the derivative of the bottom and the bottom squared. I'm not sure if, I think I might have not made it more helpful. We have 4x squared minus 2x squared minus 2. So if I simplify it, it's just 2x squared minus 2 over 4x squared. I think it's more helpful this way. If I take the numerator equal to 0, divide by 2, and then it's a difference of squares, or you can solve it. Either way, it's positive and -1. Those are my critical numbers. We also have a critical number at 0, because x can't equal 0. And there's a vertical asymptote there. It's not removable. So when I look at increasing and decreasing, if I plug in a -2, I get a positive divided by a positive. I have even exponents here, but if I factor it out, they actually end up being odd exponents. If I plug in -1/2, I get a negative answer. If I plug in +1/2, I get a negative answer. Right? Yeah. And if I plug in a big number bigger than 1, I get a positive answer. So, and at 0 anyways is an asymptote. So this is a maximum and this is a minimum. So we have a max at -1. Plug -1 in here, and you get 2 over -2, which is -1. We have a minimum at +1. +1 gives me 2 over 2, which is +1. So this is an odd function. And so there's no point of inflection, so I'm not going to bother. In terms of concavity, draw this. So the other thing that we didn't do is the end behavior. So let me look at the function again. So there are no intercepts here. If I look at the numerator equal to 0, it's impossible for the numerator to be 0. If I plug in 0 for x, it's undefined. So we have no intercepts. But the end behavior will be useful. Notice the top is more powerful than the bottom. So when I simplify that, it actually ends up being a slanted line. So this is a line that goes up to the right and down to the left. So the end behavior goes up to the right and down to the left. At 0, we have an asymptote. We have a maximum at -1, -1. And a minimum at +1, +1. And so we know that the end behavior is going up to the right, and the end behavior is it's going down to the left. And there's your graph. And we have a minimum here and a maximum there. So it increases and then decreases, it decreases and then increases, and the end behavior is right. And the behavior at the asymptote is correct, where one end goes up forever and the other end goes down forever. Number 8. Find the domain, reduced function, whole, and so on, and graph. So do everything, and then graph it. And it gives you what you need. And it gives you a point. All right, let's see if we can put this together. So this is number 8. So we're going to reduce it down to begin with. So x makes the x squared just an x. So we remove this. X can't equal 0, and at 0 creates a hole in the graph. If I plug in 0, I get the answer 0 times 4 root square root of 4, which is 0. So there's a hole at 0, 0. I also know that 4 minus x must be greater than 0, or else you'd have an imaginary number here. So if I add x to the other side, x is smaller than 4. So the domain would be from negative infinity up to 4. It's okay that x is 4 because you can take the square root of 0, but it goes from negative infinity up to 4. A number bigger than 4 would make it imaginary. If I look at the derivative, look at the numerator, and so I'm going to solve that. So I'm going to add 3x and divide by 3. Notice it's nice, they gave you what that answer is. Where is it? Right here. So 8 over 3, they give you that answer. So when I do a number line for the first derivative, only 8 over 3. Oh, and the other one I need to know, where is the derivative undefined? Is exactly at 4. But 4 is the very end of it. So there's no turning point in there because it doesn't, 4 is it. 4 is an end point. So when I plug in 4, 4, 0 is an end point and an intercept. So I just worried about here. So here's 4, and it goes to negative infinity. 8 divided by 3 is what? Not quite 3. So if I plug 3 into this derivative, I get a negative answer. And on the other side would be a positive answer. So at 8 over 3 is a maximum. So this is a relative maximum for the graph. When I look at the second derivative, if I solve this, let me show you what's going to happen. So I take the numerator equal to 0. When I solve it, there's a problem here. So 16 divided by 3 is about 5 point something. Well, that's beyond my domain restriction. So this doesn't exist on the graph. So that means there's no point of inflection. And if I plug in a number smaller than 5, whatever, the answer is going to be negative. It's concave down throughout. So the whole thing is has one concavity and it's concave down. So if I look at from negative infinity to 4, any number you plug in is going to give you a negative answer, and there's no point of inflection. So if I put all of this together, we have a hole at 0, 0. We have an x-intercept at 4. We also have a maximum at 8 divided by 3. So not quite 3 and 3.09. So somewhere there is a maximum, so not quite 3, 3.09, and that's concave down. So the left end goes down, and it ends there. And there it is. And notice the whole thing is concave down with a hole in it. Number 9. Without a calculator, find the domain, intercepts, extreme, and then graph it. All right, so to find the intercepts, I'm going to make it equal to 0. I'm going to solve that. So I can square both sides. I can add x squared and square root. So we have intercepts at positive and negative 3. We have a y-intercept. If I plug in 0 for x, the y-intercept is the square root of 9, which is 3. So we have positive and negative 3 and 0, 3. The domain, just so you know that 9 minus x squared must be greater than 0. If I factor this, it's helpful to draw a number line just for the function. and have -3 and +3 in. If I put a negative number in here, that's a positive times a negative, which is negative, so it can't be that. If I put in any number between -3 and 3, like 0, I get a positive answer. At any number bigger than 3, I get a negative answer. So that means the domain goes from -3 to +3, because that's what keeps this a positive number under the square root sign. If I take the derivative, it needs to be calculus friendly, and you'd end up being 1/2 9 minus x squared to the -1/2, and then the hook. So if I wrote it algebra friendly, it would be the 2's would cross out, and it'd just be -x over the square root of 9 minus x squared. So the only critical number is at 0. 3 and -3 are ends of the graph. So 0 makes the derivative 0. Draw a number line with 0. And it goes from -3 to +3. If I plug in a negative number, or if I plug in a positive number, so that means that 0 is a maximum. And it said there are no points of inflection, so I'm not going to do the second derivative. So at 3 and at -3, at 0, 3, so at 0 is a maximum. And that means this y-intercept is a maximum. And that's it. Connect the points. You just made a semicircle. And there it is. But you understood it in terms of increasing and decreasing, the ends of it, and that's it. You did use calculus to be able to graph it. Great job. Number 10. I think this will be our last one. And then I'll do a second video for the second half. So for number 10, make sure I'm doing this correctly. It says find the domain. Well, the domain goes from 0 to 2 pi. The x and y intercepts. So if I make it equal to 0, so at what angles are they equal to each other, but one's positive and one's negative? So that's at 3 pi over 4 and at 7 pi over 4. So at these angles, sine and cosine have the same value, but one's positive and one's negative. The y-intercept, so those are the x-intercepts. The y-intercept if you plug in 0 for x, you get 0 plus 1, so the y-intercept's at positive 1. Take the derivative, you get cosine minus sine, make it equal to 0. So when you add sine x, when are they equal to each other? So that's at pi over 4 and 5 pi over 4. And then to find where it's increasing and decreasing, sorry, it goes 0 to 2 pi. Plug in nice numbers. So if I plug in pi over 6, this one's the tricky one. So, but it's a positive and a positive. Oh, no, into the derivative. Cosine is bigger than sine at pi over 6. So it's positive. And then the signs are going to change. So we have a maximum at pi over 4 and a minimum at 5 pi over 4. So if I plug pi over 4 into here, I get root 2 over 2 and root 2 over 2, which is 2 root 2 over 2. 2's cross out. It's just root 2. For the minimum, it's at 5 pi over 4. And that's negative root 2 over 2 and negative root 2 over 2. That simplifies to just negative root 2. Next, we have to find the concavity. You're going to want a break, I think, after this question. That's negative sine x minus cosine x. So this takes us back to the intercepts. Remember, these are the same equations. So we have points of inflection here. We can do the number line for 3 pi over 4 and 7 pi over 4. And again, it goes from 0 to 2 pi. So if I put in pi over 2 into the second derivative, that's negative 1 and 0. And then the signs are going to change. So we have points of inflection here. Those are my intercepts, so that makes it easy. It's 0. So at 3 pi over 4 is 0, and at 7 pi over 4 is 0, and those are my points of inflection. So now let's put the graph together. Oh, I only need this part. So 0. I'm going to go 1 pi over 2, 1 pi, and then 1 and 5 pi over 4, and then 1 and 3 pi over 2, and then 1 and 2 pi. And it goes up. What's the maximum there? It goes up to root 2. It goes down to negative root 2. So it starts at 0, 1, goes up to root 2, and then at, what am I doing here? Pi over 2, no. So it goes up here, not here. This is where it is. The intercept's at 3 pi over 4. It goes down, and then it turns at 5 pi over 4. It goes back up. Oops, the intercept's at 7 pi over 4, so here at 5 pi over 4. What am I doing to this graph? Can I try it again? My scale. Let's try it again. I can do this. Let's do the scale better. So this is what I'm going to do. Pi over 4, pi. Sorry, pi over 2. So at pi over 4, we have a maximum at root 2. At pi over 2, there's nothing. At 3 pi over 4 is an x-intercept. Alright, I think I got it. Here at 5 pi over 4 is a minimum. This is root 2, and this is negative root 2. Here at 7 pi over 4 is a point of inflection, and then 2 pi. Yay! And so it's concave down, then concave up, and then concave down. And we have a maximum, minimum. We connect it all together. Oh, lights are going off. So that means I'm done. All right, Mr. G Math over and out. And we'll do questions 11 and on the next video. I'm really proud of you for doing your work. Till next time.